There we go. All right, I have way too many slides for 20-minute slots. I'm going to talk until the numbers turn red over there or Cristiano turns red. So the main motivation for this work here, together with my collaborators, Bill Skamarok, Prater, and Mark Taylor, has been that despite the huge amount of activity going on in transport scheme development, there's relatively little standardization of testing of these schemes. So probably the most widely used test case that we've seen quite a few times here is solid body advection, where you simply place some distribution in the flow and that's being advected along a great circle. And if you go to conferences that are not PDEs on the sphere, so if you go to a conference full of climate modelers or weather modelers, the reaction you usually get when you present your new exciting advection scheme, show this simulation, you basically get this reaction here. There are two ways to respond to this. Either you just say these people are ignorant people, they have no idea of what you're doing, or you may ask yourself, why are they reacting like this? So I've tried to take the latter approach, which I find a little bit more constructive. And there are a couple of problems with simply looking at solid body transport. So first of all, there's no deformation, it's only translation, and in nature we know that features do collapse in scale, so we're not testing that in this test case here. Partial trajectories are trivial, so people working with Lagrangian schemes have a very big advantage. And then for everybody who's interested in anything to do with weather, you're not very excited about this because there's no divergence or convergence. And a consequence of not having divergence in the flow field, at least if you use finite volume schemes, is the following. You have your equation for the density of air up here, rho is density of air, and down here you have your tracer mass equation for the tracer. Phi here is mixing ratio. If you combine these equations and set divergence equal to 0, you see that the functional form of the continuous equation for the mixing ratio itself and the density itself is exactly the same. So we do not force the modeler to distinguish between tracer mass and mixing ratio. So the first step in developing a more challenging test case suite I did together with Ram Nair. So we created this deformational flow field, so when you place a distribution in that flow, it will be stretched out into these thin filaments, and at the same time it's being transported eastward. So we have the flow field, and then I teamed together with the people on the first slide here to try and design a test case suite to facilitate scheme intercomparison. In particular, we provide specific guidelines on resolution. We even provide guidelines on plotting, so it's easier to compare the different schemes. But also in general, we wanted to test a wide range of aspects of accuracy that we believe are important for geophysical fluid dynamics, but we also wanted it to make it minimal. So if you look at the shallow water test case, Swedish have 7 tests, I think. I think very few people publish results from all of them. So in this case, we're trying to keep things as simple as possible. So we only have 2 analytical wind fields, and we have 4 initial conditions. And the initial conditions vary from infinitely smooth, the Gaussian hills, to C1, so quasi-smooth, to totally unsmooth. And then we also have an initial condition that's a nonlinear function of the cosine bells here, and that will become clear in just a moment why we do that. So basically grouped our different tests into 6 different tests, designed to first of all assess the what I would call the optimal numerical order of convergence. So we use C infinity initial conditions, and I'm approaching this from a global climate modeler's point of view. So I want to know what is the conversion of the scheme in this resolution range here. So from about 3-degree paleoclimate resolution down to what I would call cutting edge climate resolutions, which are about 1/4 degree or 0.3 degrees, at least today. Then I'm not just interested in convergence, I also want to know the absolute error. So I would like to know at what resolution you need to run to obtain some level of accuracy. Then we also look at this newer test here that Michael Prater suggested, namely to look at the ability of the transport scheme to preserve filaments without knowing the analytical solution. ability of the scheme to transport rough distributions, and then we have a newer kind of test here where we don't test the transport scheme in single tracer setup, but we would like to test how well does the scheme maintain pre-existing functional relations between tracers. So this is a two-tracer test. So we do all this with this flow field down here, which is non-divergent, and then we have added a sixth test case, which involves a divergent flow field, just to make sure the modeler has considered or forced the modeler to consider the coupling between tracer mass and the mass of air. So last year we invited anybody who wanted to come to NCAR to run this test case suite. And we're currently writing up these results in a paper, and I thought about 5-6 schemes would contribute to this, but the list is way longer than that. So we had everything from lat long finite volume schemes. We have a Donner scheme here, the claw scheme. We have my own scheme. We had a traditional semi-Lagrangian scheme on the cube sphere participating. We had the Hell scheme out of Copenhagen. We have the spectral element method participating, the icon group. Also the scheme that Peter Busler talked about, MPAS, Professor Enomoto's scheme, and Paul Ulrich was there with his finite volume scheme. Then we have a new fully conservative Lagrangian method out of China, and Michael Prater was there with his moment scheme. So I'm going to show some results involving these schemes. So the first test, we simply ask, as I mentioned before, you run the test case suite with infinitely smooth initial condition. So if you do that, you should get the optimal order of convergence. Again, I'm looking at this resolution range for the reasons I told you before. So you do the least squared fit to these lines, and then you get an idea of the numerical order of convergence of the scheme. And you see that we have everything from near first order to seventh order. We don't have the 17th order scheme here, but I should mention the red lines here is the unlimited scheme. The green lines here, that's when you have a shape-preserving filter invoked. And not surprisingly, shape-preserving filters can have an effect on convergence rates, and some schemes suffer more from the limiter than other schemes do. Not that surprising. The minimal resolution, you take the convergence plot, draw a horizontal line, and then you ask, at what resolution do you cross that line? I chose that line taking a selfish approach. I took my own scheme at 1.5 degrees, and then I asked people, when do you match my scheme at 1.5 degrees with respect to L2 aeronorms? And again, same plot as before. And you see that the minimal resolution for these schemes here vary greatly, all the way from 0.2 to 2.3 degrees. And one reason why I am particularly interested in these minimal resolution is that if you come at this from a climate modeling perspective, historically, every time we change the resolution in the climate model, we spend a lot of time tuning physics, etc. So I'm interested at the accuracy of the method at a given resolution. So now to a newer test. Since it's newer, let me motivate it. So perhaps the best motivator for this is if you look at long-lived species in the stratosphere, for example, N2O, NOY, or the CFCs, and you plot these against each other on a scatter plot, as done here. So these are aircraft observations. Then you see that despite the large range of scale of motion in the stratosphere, ranging from 1,000 kilometers down to a couple, you see that the data collapse to these very compact curves here. They're slightly nonlinear. These compact curves here can be physically or chemically important. Perhaps the best example is it's been used to quantify chemical ozone loss. So obviously, you would like your scheme to not perturb these functional relations in unphysical ways. Related to this problem is also if you look at families of species in the atmosphere, such as total organic and inorganic chlorine, they usually sum up to a constant or something close to it. although that the individual species here react very vigorously between each other. So you don't want your transport scheme to perturb that sum either. And similar arguments can be made for aerosol cloud interactions. Linear correlations has been discussed for quite a while. Lin and Root and Fuber and McIntyre discussed that in their papers, and there's a large family of at least finite volume schemes that do not perturb linear correlations. However, when you take nonlinear correlations, it's only Lagrangian schemes that are able to maintain those relationships. So the test case start we're doing, we are taking the cosine Bell initial conditions, and then we initialize the other tracer by relating this with a nonlinear formula. So we use this parabolic relationship here. That means if you take each point in this domain here, plot it in a scatter plot, all your points in the domain lie on this parabolic curve. So when you start your simulation, and you're not using a Lagrangian scheme, and you're turning off any kind of explicit or parasite mixing, then these points here will start to deviate from this pre-existing functional relationship. And to give you a feel of, first of all, let me make some arguments about how these scatter points should move. If you look at nature and you have two air masses mixing, let's say this parcel is looking at one air mass, this one in another one. When they mix, then they will start to move towards each other on a straight line. So if you take the combination of all straight lines between all points in this curve, you end up with this red area here, which is referred to as the convex hull. So if my scatter points move into that area here, I refer to that as real mixing, since it resembles what's happening in the real atmosphere. Anything else is spurious unmixing. So to give you a feel how this works, here's an animation using my own scheme. First of all, if you take a point here, a background value point, that's the point located up here, and your extreme and your distributions are located down here. So obviously, diffusion will tend to make the points down here move up along the mixing curve. What you also see is that points here, even though I'm running with a shape-preserving scheme, I still have points moving away from the convex hull. I have unmixing in that direction. Fuban and McIntyre showed that, or demonstrated mathematically, that the only schemes that will guarantee that you don't have any unmixing in that direction are first-order schemes. So if you can't accept first-order scheme accuracy, then we have to accept some level of unmixing. What my shape-preserving filter does is that I do not expand the range of the initial conditions. So you see you have no points going outside this square. If they do that, that's poison to parameterizations usually. So here's a scatter plots for a range of cube sphere models. This is 1 degree models, 1.5 degree models, unlimited in the first column, shape preserve in second, and then repeat that for 0.75 degrees. And obviously you can see what I alluded to before. If you have no limiter on, you start producing or expanding the range of the initial conditions here. Some do more than others. Here are some results from regular latitude longitude models. So perhaps not surprisingly, the Prater scheme that preserves second order moments does exceptionally well with respect to this metric here. Also, you can also in these scatter plots see that shape-preserving schemes such as the dimensionally split scheme in CAM-FV still does produce a little bit of overshooting, and that is due to the dimensionally split nature of how that limiter has been implemented. And similarly, here are results for different icosahedral models. So you can get a lot of just looking at these scatter plots, but you can also quantify the mixing. We do that in the following way. So define a distance functions here, which is the normalized distance between my scatter point and then the point on the pre-existing functional curve that's closest to the scatter point. That's this dk. And I limit that by the range of the initial conditions. So if you have a point out here, the closest point on the curve will be the one up here and not the one located up here if you extend the curve. all of those are area weighted, and then I categorize the different mixings here into these categories here, A, B, and C. So real mixing, range preserving, unmixing, and then overshooting. The nice thing about this diagnostic is that you do not need an analytical solution for this. So you can take any 2D, 3D model, plot in two traces that are rated nonlinearly, and you can compute these diagnostics. So here's a real mixing at 1.5 degrees for the different schemes. I've normalized the y-axis here with the mixing for my own scheme at 1.5 degree just to have some kind of threshold value. Please note that the y-axis here is logarithmic, so there's a huge spread in the amount of mixing that these different schemes produce. Also, what we see is that there's a tendency, or in general, the real mixing for the scheme with a shape-preserving limiter is actually less than it is for the scheme without the unmixing. So this diagnostic seems to capture that something physical. You know, if you have a shape-preserving limiter, that's usually considered a more physical solution than the one without, and it does pull the solution. Or this diagnostic seem to capture that, and you see similar results in the unmixing category, and the overshooting obviously is 0 for the shape-preserving limiters. Had I tried to do this test with the most popular test, namely the solid body advection of some distribution, this test would not have been very exciting. You know, basically all the scatter points lie on the curve. So it's very important for this test case suite here that you have a large amount of deformation. So basically well-resolved initial conditions stretch into not very well-resolved features. Okay, now to the filament diagnostic that Michael Prater came up with. Again, that's a diagnostic that does not need an analytical solution. However, it does rely on the fact that, or it does rely on having a non-divergent flow field. So if you have a non-divergent flow field, we know that if you follow Lagrangian areas, they don't change. So if you measure the area for which the tracer distribution is above some threshold, that should be constant in time. So the area above, for example, 0.8 in the initial condition should be the same halfway through the simulation. So we use this diagnostic here. We put a factor of 100 in front, and then you normalize with the initial condition. So the perfect scheme should simply produce this filament diagnostic as a constant for any of these threshold values. So up here you have I've shown a very diffusive scheme, a first order scheme. So obviously the area where the threshold value is, or the mixing ratio is above a large threshold value is 0. And you have a lot of diffusion. That means the area for low threshold values goes up. And as you go to higher order, you see you pull these out further. So here are some results for some of the schemes that participated in the workshop. And I think the most interesting result here is that if you use a mass fixer, as was done in this cube sphere, traditional similar Lagrangian scheme, you see that the filament diagnostic gets very, very noisy. You don't have this almost monotone variation in the filament diagnostic. Okay, you're not turning red yet? Almost. Okay. Just very, very quickly, we also wanted to challenge limiters in the scheme, so we put a rough discontinuous initial condition in the flow. And then we've asked all the modelers to provide me data for that flow. And the nice thing here, I think, is that now we have everybody plotting with exactly the same color scale, so it makes it a lot easier to compare the different solutions. And I'll stop here.
One of the things that'd be nice to get out of a study like this, or any other study with test problems, is design principles. What design principles examples for schemes have you gotten out of this?
You mean by from which
I'll give you an
the
example
derivations?
I'll give you an example from ancient history. When limiters were developed in the mid to late 70s, it was quickly realized that low phase error for the underlying unlimited advection scheme determined how sharp the discontinuities would be represented in a limited scheme.
Mm-hmm.
So that's a design principle.
Mm-hmm.
It applies very broadly. Are there analogous design principles that are emerging from this study?
No, we just look at results here. The thing I didn't mention here that we obviously do not target computational efficiency directly here, but we do ask people to lay out the basic design of the schemes in terms of how many functional evaluation do you need, how big is your halo, how often do you need to communicate, etc. But not design principles in that sense.
You mentioned the mass fixer role. Is that independent of how you fix the max? The noisiness?
We only had
Are
one
you
scheme
with
with
a
a mass fixer, so I don't know.
Do you know how they do they set
This is
that?
a global
max fixer, and the adjustment is just
Yeah, just everything. But you're welcome to submit results for it.
Any more questions? None, but thank Peter again.